Today we're going to continue talking about vectors, so pick up the practice worksheet from the blue basket. Begin the warm-up for 4.28 in Delta Math. Let's review some of the vocabulary. We'll start with scalar. A scalar is any quantity in physics that has magnitude only. Some examples of scalars are speed, distance, and age. The magnitude, here's an example, 35 miles per hour, just shows the speed. It doesn't show direction. A distance of 25 meters shows length, but there's no direction. And then age, 16 years, shows how many years. Okay, so it's a measurement. A vector is a quantity that has both magnitude and direction. So some vector examples are velocity. If we say 35 miles per hour going north, we're adding in that direction. Acceleration, 10 miles per hour squared south. And displacement, 20 miles east. So again, magnitude and direction. Vector quantities can be identified by bold type and a symbol. So we typically see them written this way. So vector V would be 25 miles or meters per second northeast. So it shows magnitude and direction. Vectors are represented by drawing arrows. The length and the direction of the vector should be drawn to a reasonable scale size and show its magnitude. When we're going in the same direction, when two vectors point in the same direction, you simply add them together. And we have a resultant or a sum vector. Now the resultant goes from the tail of A to the head of B. We always go from head to tail. We can't put the tips together or the tails together. So let's practice what we learned on Thursday. A man is going to walk 46.5 miles east, then another 20 miles east. So he's going in the same direction. We're going to calculate his displacement relative to where he started. So I typically draw a picture that helps me visualize what we're doing, and we're going to pretty much stick with 2 dimensions. And with 2 dimensions, we have north, south, east, or west, and so we can put that on a coordinate plane. But we can just draw this going 46.5 miles east. That's the red arrow. And then add to that head the tail of the next vector, 20 miles east, going in the same direction. Notice the same direction. So you can line them up head to tail and just add those two together. 46.5 and 20 gives us the resultant of 66.5 miles. Subtraction is when two vectors point in opposite directions, so you simply subtract them. All right, so let's practice with this and just visualize it. 46.5 miles east, then another 20 miles west. So east and west are in opposite directions. We want to calculate that displacement. So again, we're going to put head to tail, okay, with each vector. So we're going to go forward 46.5 miles east, and then backward 20 miles west. So 46.5 minus 20 is 26.5. Our resultant vector is 26.5 miles, and it's pointing east. Now the graphical method, when we align vectors head to tail and then draw the resultant from the tail of the first to the head of the last, that red vector is going to be our resultant, where we ended up. So we're going to add vector A to vector B. We're going to draw a start point. We're going to decide on a scale. Draw to scale. Vector B's tail begins at vector A's head. We're going to draw the connecting initial start to the head of B and have the resultant. Okay, going up to the head of the last vector. So that's good. D is going to be the distance of our resultant. Okay, now I can take those and I can rearrange them. I can pull them down and rearrange them as long as I'm going from head to tail, and I'm still going to get the same resultant. So that means that vector addition is commutative. Non-collinear vectors are when two vectors are perpendicular to each other. And in that case, we can use the Pythagorean theorem. So let's practice one of those problems. We have a man traveling 120 kilometers east, then 160 kilometers north. We want to calculate his displacement. So let's draw that. We're going to start here at the bottom. That red line is our horizontal component. So we're going 125 kilometers east and then 160 kilometers north. And we're going to finish up at the top. Our resultant is going to be that hypotenuse of that triangle that we've drawn. So we would simply use the Pythagorean theorem. Okay, so c squared equals a squared plus b squared. Take the square root of both sides. Plug in your values, and we get our resultant equaling 200 kilometers. All right, what about direction? In the example, displacement is asked for, and since it's a vector quantity, we need to report its direction. Okay, now notice when drawing a right triangle, it conveys some type of motion. Okay, and remember, we must always draw our components head to toe. The arrows can't come together, and the tails can't come together. And we're going to relate in 2 dimensions our coordinate plane to the north, south, east, and west directions on a compass. So it's important when we talk about direction, okay, we always start out at 0, which is east, and if we go up, we're going north of east. But if I start north at 90 degrees and go down, I'm talking about east of north. Let's draw another vector in that third quadrant. And if you're trying to describe your angle, I'm looking at this angle up here, this is going to be south of west or west of south. Let's look in that second quadrant. This angle is north of west, and this angle is west of north. Some things we have to get used to when we're talking about direction. Okay, and then in the fourth quadrant, I have south of east, and I have east of south. So in our example, we're looking at north of east when we describe direction. Now there's a difference between northwest and west of north. So this is 30 degrees northwest. That's north of west. But this is 30 degrees west of north. We're not as much used to describing it this way, west of north, but we are used to hearing northwest. Now we need a value, an angle. So just putting north of east is not good enough. We need to know that measurement. So let's look at what we have here. Okay, let's draw our triangle. And I want to know what this angle measurement here is, what theta is. So let's think about what we know. We know our trig functions. So I have the measurement 120 kilometers and 160 kilometers and 200 kilometers. So I have all 3 measurements. So I'm going to choose tangent. Tangent is TOA, opposite over adjacent. So from the orientation of theta, the opposite side is 160. So let's put 160 here. And the adjacent side is 120. So we'll put 120 here. So the tangent is 160 divided by 120. And if you put that in the calculator, I would probably use 16 over 12 or reduce this fraction. If you put it in the calculator, you have 1.33. So you have an approximation. All right, so we have theta. If we want to find theta, we're going to use the inverse tangent function, and we apply that to both sides. So when we apply the inverse tangent function to the left, we have theta. Theta comes out. So let's apply the inverse tangent function on your calculator to 1.33, which we found up here, and that will give us the angle measurement of theta, which is 53.1 degrees. Practice doing this on your calculator. Write it down for reference. And you can also use, because you have all three sides in one angle, you can use different trig functions. So to find the value of the angle, we use a trig function called the tangent in this example. So your complete final answer is, remember, we need to have direction and we need to have magnitude. So we have the 200 kilometers as our magnitude, and the direction is 53.1 degrees north of east. So what are your missing components? Suppose a person walked 65 miles, 25 degrees east of north. What were his horizontal and vertical components? So the goal is to always make a right triangle. And then we're going to solve for components. And we often use the trig functions, if we can, sine and cosine. All right, so let's draw that. So the person walks 25 degrees east of north. Okay, so here's north. East of north is going to be this angle here. Okay, and the length is 65 miles. So that angle 25 degrees is east of north. Let's make sure that we put that in the right location. All right, here's our vertical direction. We want to find that vertical component, and we want to find the horizontal component. Okay, so we're going to make that right triangle, and let's look at what we have. Okay, we're going to use sine and cosine. Theta is our 25 degrees. So cosine of 25 is going to be the adjacent over the hypotenuse. Sine of theta is going to be opposite over hypotenuse. Or we can solve for the adjacent or the vertical component with cosine. Adjacent is going to be our vertical component, looking at our angle theta. So we're solving for adjacent. We're going to multiply both sides by the hypotenuse. Multiplying by the hypotenuse on the right side is going to cancel that denominator. And then on the left-hand side is going to be hypotenuse times cosine of theta is equal to the adjacent side. Okay, for sine of theta, that's going to give us opposite over hypotenuse. Opposite over hypotenuse. Now we know what theta is, so sine of 25 degrees. We're looking for the opposite side, multiply both sides by the hypotenuse, and we get the opposite side equals the hypotenuse times the sine of theta, which is 25 degrees. So the adjacent, or the vertical component, is 65 cosine 25, and that's equal to 58.91 meters north. The opposite is 65 sine 25, or 27.47 meters east. All right, another example, we have a bear searching for food that wanders 35 meters east and then 20 meters north. Frustrated, he wanders another 12 meters west and then 6 meters south. Calculate the bear's displacement. All right, so let's draw that. 35 meters east, 20 meters north, 12 meters west, and 6 meters south. All right, look at the purple and the red. We're going to subtract those. They're going in opposite directions. Okay, so 35 minus 12. Our displacement is 23. Now let's go vertically. We're going to go up with the blue 20, down with the green 6. So 20 minus 6 is 14. So now we can draw these two vectors and then show the displacement. And we should end up at the same place. That's going to be our resultant. All right, to find the displacement, I'm going to use the Pythagorean theorem. So the resultant is equal to the square root of 14 squared plus 23 squared, and that's going to be approximately 26.93 meters. Okay, now that I have all three of those sides, I have the legs and the hypotenuse, which is the resultant. I'm going to use my tangent function. Tangent of theta, here's theta, opposite over adjacent, or 14 over 23, is 0.6087. And then to get theta, to find out what theta is, we need to use our inverse tangent function. That's going to make theta drop out. So the inverse tangent of 14 over 23, or 0.6087, is 31.3 degrees. So our final answer is 26.93 meters is the distance of the resultant, and it is 31.3 degrees north of east. In this example, a boat moves with a velocity of 15 meters per second north in a river which flows with the velocity of 8 meters per second west. Calculate the boat's resultant velocity with respect to due north. So let's draw that. North, south, east, west. Okay. Due north is that blue arrow. Okay, so it's traveling 15 meters per second north. Okay, and then our second vector is 8 meters west. All right, let's calculate the resultant using the Pythagorean theorem. The resultant vector is going to be 8 squared plus 15 squared. Find the square root of that, and that's 17 meters per second. Okay, the tangent of theta, so here's theta, is going to be opposite over adjacent, or 8 over 15. To find theta, use the inverse tangent function, and we get 28.1 degrees. So our final answer is 17 meters per second at 28.1 degrees. And then we have to describe what this is. This is west of north. Another example, we have a plane that moves with a velocity of 63.5 meters per second at 32 degrees south of east. So let's sketch that and calculate the plane's horizontal and vertical velocity components. All right, we have a vector here, 63.5 meters per second at 32 degrees south of east. Okay, we want the horizontal component here and the vertical component here. So let's use the cosine function. We have that angle measurement. So cosine of 32 is equal to adjacent. Adjacent, we don't know, over hypotenuse, 63.5. Okay, so I want to solve for adjacent, so I'm going to multiply by the hypotenuse on both sides. So the adjacent is equal to the hypotenuse times the cosine of theta. So let's plug in what we know. We know the cosine, we know theta is 32. We know that the adjacent side is, we don't know the adjacent side, but we do know the hypotenuse is 63.5. So the horizontal component is 63.5 times the cosine of 32, and that's going to be 53.85 meters per second east. And then the opposite, we're going to use the sine. So we have 32 degrees here, the opposite over hypotenuse. So we know the hypotenuse, we know theta, so I'm going to multiply both sides by the hypotenuse and get opposite equals hypotenuse sine of theta. Okay, put that in your calculator and you'll get 33.64 meters per second south. Another example, a storm system moves 5,000 kilometers due east, then shifts course at 40 degrees north of east for 1,500 kilometers. calculate the storm's resultant displacement. All right, so we're going to draw this due east. Okay, it shifts course at 40 degrees north of east for 1,500 kilometers. So we want to know that vertical component and that horizontal component. I'm going to use the cosine and the sine functions. So cosine is adjacent over hypotenuse, sine is opposite over hypotenuse. We know the angle measurement, so we're going to go ahead and substitute 40 in for theta. Solve for adjacent, so it's going to be cosine of 40 times 1,500, sine of 40 times 1,500 to get that vertical and horizontal components, like we did earlier. All right, we're going to use our Pythagorean theorem. Our final answer is 6,224.2 kilometers at 8.92 degrees north of east. All right, other things in travel that change direction are headwind, tailwind, and crosswind. So again, this is just an illustration of it's often used in flight